Antropol, a distinguished physicist and professor at the IISER Pune, to the stage. Please join me in welcoming him as he shares his insights on the fascinating advancement in quantum technologies.
Thank you very much for the kind introduction, and thanks to the organizers for inviting me for presenting at this symposium. Okay, my talk is going to be slightly different. I'm going to delve into the slight technical details about one particular platform of quantum computing, and in this talk I'm going to tell you about how trapped ions can be used for doing quantum computing. Just yesterday, following up with what Mr. Raghavan talked about, just yesterday there was a news article about some work that was published in Nature Communications recently, where they used a trapped ion quantum computer to actually do a verifiable quantum random sampling. So I haven't gone through the details of that, but this work actually demonstrated that one can actually do a verifiable quantum random sampling. They used this particular platform. Since it just came last night, I didn't get time to read the paper, otherwise I would have put the details in this talk about how they did that. Now, apart from, many times when many people look at a quantum computer, they see this image of hanging chandelier, right? Which is basically one particular platform of quantum computing. Just because I think IBM took the initiative to kind of push this platform a lot. But just for your information, for some of you who may not know, there are quite a few other successful platforms that are coming up, and of which trapped ions and atoms are in the forefront of these technologies. Actually, some of the most cleanest of the demonstrations were done in, say, neutral atoms and trapped ions. I'm not saying that these are superior, I'm just saying that these are also at the forefront together with the superconducting quantum computer, superconducting platform. And then, of course, there are other things which are coming up, solid-state qubits-based quantum processors, but there is still some way to go. For example, semiconducting qubits or electrons trapped in a two-dimensional structure in a solid-state system. Okay, I'll focus on trapped ions, although I should have added neutral atoms also, because they have also shown very good promise in the recent times. But I will, since time is less, I thought I'll focus on one particular platform. So I'll do a quick introduction of what ion traps are and how these ion traps can be used for quantum computing. And I'll ask some of you to excuse me, they must have heard some portions of this talk before, but yeah. Okay, so here is a picture of both the companies which have used atoms as well as ions separately for demonstrating quantum advantage, or at least demonstrating the usability and usefulness of these platforms. So the top ones are a few companies. Okay, there are a couple more companies which are not listed here, like Oxford Ionics and things like that. And then you have these companies. Okay, there is Pascal also from France, which is also involved in using trapped atoms, neutral atoms, whereas these are ions which are trapped in electrodynamic traps, whereas these neutral atoms are trapped in optical tweezers, an array of optical tweezers formed by various techniques. Now, just to give you an example of what these trapped ion qubits can do. So this is an earlier version of a 32-qubit system which was developed by Quantinuum. Quantinuum was a spin-off from Honeywell, and this, if you look at it, the qubit numbers are not so promising, okay? If you compare with the Velo or whatever, these were just 32 qubits. But the things that are very important to look at are these numbers here, which basically give you the quality of these qubits, the single qubit, the fidelities and infidelities of these different operations that you do on the qubits, the state preparation and measurement error of these qubits, etc. Look at that. They are way below a fraction of a percentage, which are much better than some other types of qubits. Now they have a latest one which now they have, it's called the H2, and that has these numbers, okay? These are the number of qubits, 56. Okay, the quantum volume, whatever it means, it basically characterizes the width of the circuit, the depth of the circuit, the number of gate operations that you can do within the coherence time of the qubit, and the connectivity of how many qubits are connected together. All these you do a complex calculation and come up with some number, which is again just for the namesake to compare across different platforms and look at this fidelity number. So single qubit fidelity is like 99.997 and the 2 qubit fidelity is again over 99%. So this gives you an idea about how good these qubits are. And unlike, for example, superconducting qubits, each qubit has the same property like any other qubit. You go anywhere in the universe, you have million of them, billion of them, all of these will have the same property. Unlike, for example, superconducting qubits have to be fabricated on a chip. Okay, so this introduces all kinds of uncertainties in the fabrication process, the way you deposit, the quality of the substrate, the dimensional tolerances, all these kind of things, they vary from one Josephson junction to the other that you fabricate to make these qubits. So there it becomes extremely challenging to have state-of-the-art fabrication techniques which guarantee reproducible fabrication of these qubits. So that aspect is not present with these particular qubits. Okay, this is an example of a trapped ion surface ion trap which is sitting inside here from this company called IonQ. And they have a 32 qubits one. And now this Austrian company, Austrian Alpine Quantum Technology, which is a spin-off from the University of Innsbruck, where this ion trap work has been going on for a long time. In fact, I was working in that university more than 20 years ago, well, when this work had started. So you can imagine, only in the recent times this hype has picked up, but the work on all these has been going on for over many decades. Again, some things that people have done using these qubits, though the number is small, fine. Okay, I don't have to tell this, everybody knows why qubits are superior, why they are projected to be more superior than classical bits to perform computers. Other than doing computation, there are many other things that one can also use use quantum mechanical systems, quantum mechanical two-level systems, the qubits, the so-called qubits, can be used for a variety of applications. You can build extremely precise clocks which will not even lose 1 second over the entire age of the universe, and which these kind of clocks have a potential to give, for example, one of the things is giving extremely high precision GPS navigation, one of the examples. Other than many, there are many more applications. Okay, so just for students, not for the experts here. So what is a classical bit? Classical bit is basically all the flip-flops that you have in a classical processor. Each flip-flop is made out of some gates, and each gate is made out of some set of transistors. The state, the logical 1 or 0 state in this classical bits is nothing but just some transistors switching on and off. And you define certain voltage levels which you say, okay, below this voltage level threshold, I call it a 0. Above certain threshold, I call it a 1. So depending on what logic family you have different types of voltage levels. And this is what it is, classical bit. And then you put them together and build a memory, which is basically a basic building block of this memory, is a flip-flop. Unlike this, which has only 2 possible states, in a quantum system, for example, that is this one is just some low-lying energy levels of when you excite electron from the ground state to some low-lying excited levels. This is just an example of a calcium ion. You can have it for any ion, any atom or ion. So these are what are called as a qubit states, meaning the ground state is your 0, the excited state is your 1, and then because of this quantum mechanical properties, you can not only have the state well defined in one particular state, but you can also have superpositions. You can also, if you have more than one such qubit, you can also have an entangled state between the qubits and so on. For photons, you can define in different bases. So it could, of polarization, for example, it could be horizontally polarized photon or a vertically polarized light, which can be used as your states of these photons, which are your qubit state. You can also have right circularly polarized or left circularly polarized. And then you define this, the qubit state, not only, you can define it on a sphere, where you define the poles of the sphere as the 0 or 1, and then any possible combination of these zeros and 1, the superposition state, can be defined by a vector on the sphere. Okay, and that's your quantum state. Now, there are two broad classifications of this systems which can be used for quantum computing. One, the broad class of systems are quantum optic systems, which basically use either atoms or ions in optical traps or electrodynamic traps, or you can have an atom and a photon system in a strongly coupled system like a cavity QPD system, where you have an atom inside an extremely high finesse optical cavity where you have a photon which stays there for a very long time interacting with the two-level atom. Or you can also use entangled photons which are generated through down conversion, like the way you would have seen these pictures of these two cones which intersect when light is passed through certain crystals which are cut along certain axes, and then you can generate entangled photons in such a system. Then the other broad class of systems are the solid state systems. Solid state systems have the greatest advantage of a solid state system is that if at all in the future sometime, if they work at room temperature, you can make them like a chip and put it on a card. That is the biggest advantage, and you can fabricate as many qubits as you want, but there are a lot of challenges. So mainly in the solid state system, the most successful, the only successful one has been so far Josephson junctions, and then electrons which are trapped in electrons in a 2D electron gas system. They can be trapped like islands with electrodes, and then you can do this quantum state manipulation. Then people are talking about using nitrogen vacancy centers in diamonds also for quantum computing, but this is a bit more challenging, but this is still kind of being thought about. So what should this, any quantum mechanical two-level system, what are the criteria that it should satisfy in order to qualify for a qubit? Okay. First and foremost is you should be able to decide, you should be able to set my initial state, which means if I want the qubits initially in 1, I should be able to initialize them to 1, or if I want them in 0, I should be able to initialize them in 0. That is the most important, the first one. The second one is coherence times. See, any of these two-level systems, once you excite say electron to an excited state, it's going to decay back within certain time. There is a lifetime associated with any of these quantum two-level systems because of certain fundamental interactions that these two-level systems go through. They will decay eventually down, to the ground state. Now, this time is the lifetime. Now, coherence time can be thought of in some vague sense to be this excited state lifetime, that kind of that can be compared with that, but it's not in the strictest sense. One can assume you can assume that this time has to be long, but long in terms of what? For example, superconducting qubits have coherence times of 100 microseconds. These atoms can have lifetimes of order of several seconds. and the coherence times are also matching up, coming very close to the natural lifetime of these ions, atoms these days. Now, what do you call, I mean, that is 100 microseconds, this is second. Which one is better? That is not the point. The point is, what is your gate time? If my gate time is 1 nanosecond, I can execute so many gates within 100 microseconds. In case of atoms, the gate times are longer. They are in the range of several tens of microseconds. So the ratio between the coherence time and the gate time is what is very important. So, and third thing is you should have universal set of gates. For qubits, these are quantum gates. In classical computers, you know that NAND gates are universal gates. Because once you have a NAND gate, you can build any gates, and from these gates you can build memories, you can build shift registers, you can build these counters, whatnot you can build. Same thing with the qubits, you need to have certain set of basic gates which are called universal gates, and in case of qubits it is single qubit rotation, which means you should be able to define from zeros and one, you should be able, the block vector you should be able to rotate anywhere on the block sphere, and second is you should be able to have a executed 2 qubit gate, meaning one of those gates is a controlled NOT gate, which is the universal gate for quantum computers. Once you have these 2 gates, then you can construct any types of gates. You can build a quantum circuit and then execute. And you should have a scalable system. I should be able to increase the number of qubits. And then, of course, if you are interested in networking quantum chips like the processors, you can obviously do a classical information transfer through some electrical wire from one computer to the other to tell the states of whatever qubits. But more than that, what is important is that if you want to really scale up the system by actually connecting them with wherein they can transfer quantum information from one processor to the other, you need additional requirements. You should be able to have a node which can do an interconversion between the information of a physical stationary qubit to a qubit that can go from one place to the other, a flying qubit. Now that, and the channel should be no loss. There shouldn't be any loss in this channel. So the only thing that satisfies this is a photon. So you should be able to transfer the internal information of an atom or a qubit, any qubit, onto a photon. This photon could be in any frequency range depending on what physical qubit you are talking about. And you should, like, if once you talk about light, it can be transmitted over fibers and you can connect to processors. So since I'm talking about ion traps, what are these ions? Okay, this is a real picture. This is from the Innsbruck group. This is a fluorescence image of 3 ions. These are physically separated by maybe a few micrometers from each other, 5 microns or so, and you can create a chain of this. These ions, since they repel each other, so there is a external confining electric field which confines these atoms, so these don't fly away. And then because they repel each other because of Coulomb repulsion, they are all positively charged, so they stay away from each other. So it acts like this, masses attached with springs. So if you move one of them, they all start shaking. And then you can imagine that this system is like a molecule, a linear molecule with 3 atoms, right? So once you shake one of them, then because of this bond, these bonds will start stretching and contracting. Then you excite different vibrational modes, and that is important for executing these 2 qubit gates in a ion trap quantum. So it's like this is a harmonic trapping potential where you confine these ions, and then once you excite them, different vibrational modes. These are different vibrational modes of these string of ions. Okay, so how are these ions trapped? So the first thing that was invented was this Paul trap. It is basically a 3-dimensional trap. This is a cross section. So the central electrode is kept at one potential and the outer electrodes are kept at the other potential. And then you oscillate between positive and negative. Okay, you apply radio frequency between this two and the outer, this ring electrode, and you can confine ions in the middle. Okay, so this looks like the electromagnetic potential. I'll come to that. Electrostatic potential. You cannot create a minima in free space. Okay, because I'll tell you why. So the potential looks like a saddle potential. So in one direction it will be minima, in the other direction it's like a maxima. So it will roll off. If you put a ball, it will roll off. So instead, if you rotate the saddle, you will stabilize the ball in the middle. Same thing is done here by applying a time-varying electric field between these electrodes. You can actually trap it. Now this is a three-dimensional spherical trap. You can have a linear trap also. I'll come to this later. So in a spherical trap, the electric potential, you can write it in that form. I mean, excuse me for some of you, if you don't understand, ignore it. It's not, maybe the students would find it interesting or might get some idea from this. So the electric potential is basically a quadrupole potential along the three directions, Ri, which is Rx, I mean, along the X, Y, and Z direction. You can write down the electric field in the center of that. And that's your Laplace equation for that electric potential. Now, the point is, this equation, it tells that the sum of all the coefficients have to be 0. Okay? So, which means some of them will be positive, some of them will be negative, have to be negative. So, essentially what happens is that you generate a potential which is basically like this saddle potential. Okay? Now, you cannot stabilize a charge with just a static potential. You have to do something else. You have to rotate that saddle. The way it is done is this phi naught, you apply a time varying component to it. So you apply an AC field and you start rotating that saddle so the ball stabilizes. So you can trap this ion. In this case, the ion is trapped inside. And then you do all kinds of things like you solve this equation of motion, and then you end up with some complicated equations, nonlinear equations, which essentially tell you that an ion can be stabilized only for certain set of parameters of the frequency and the amplitude. And from these equations you get certain regions for these parameters A and Q, where you have regions where your ion can be stable. So if you, depending on what species you choose, calcium, ytterbium, barium, beryllium, any of these ions which you want to trap, which have accessible laser cooling transitions, you have to calculate what, for the given geometry, you have to calculate what my parameters A and Q should be, which is decided by the DC potential, the frequency of the RF that you apply, and you get the, for the given geometry, you calculate those and design your trap. Now, what happens is that now you're rotating this saddle, right? And then you're stabilizing the ball. So if you do a time averaging of such a potential, you get a, effectively time average, you get a potential well, basically, a ball, right? If you do a time averaging. So that is called as, what is called as a pseudo potential, this side. This is what you get when once you do the time averaging and all that, you get this psi. And then this ion is, the charged particle is not stable, okay? Because you are rotating at this radio frequency, whatever frequency, it has a small motion associated with the radio frequency. And then there is a overall motion in this time average potential, the ion or the charged particle is going to do an oscillation in the pseudo potential. So these lead to different kinds of motion of this particle. One is a micro motion, which comes about because of the rotation of that saddle that we are talking about. And if the saddle is not rotating exactly along the center, then the ball will get, it will keep moving around at the rotation frequency. So it is very important to have very good geometrical tolerances for this trap so that you don't get micro motion, because that leads to heating of these ions. Fine. The other type of trap which we are interested in for trapping is a linear Paul trap. The earlier one was a spherical one. which is of no use for quantum computing in general, but but this is very useful for doing very precision spectroscopy experiments on ions. The one which we are interested in for a quantum computing thing is something like that. So this is a two-dimensional one. If you take away these end caps, and look at the center, the potential is minimum along the line in between these electrodes, 4 electrodes. And that's where you trap the ions. And then by applying a DC potential from the side, you confine the ions only in the central region of this trap. Okay? Now again, for this geometry also, you can write the equations of motions and parameterize those equations and get these stability parameters. Stability parameter, which is basically one parameter. It is same along the x and y in the radial plane, in this along this cross section. In the z direction, you just have a static potential, which actually so this b along the radial direction. This is along the radial direction. Sorry, along the axial direction. It's dependent also on the tip voltages. If somebody is interested in the details, we can talk later or drop an email. I'll explain to you. But just as a quick this thing for the students, I wanted to show this. Okay. Forget about all that. Just concentrate on these numbers here. For example, if you had a trap where the distance between these electrodes is about 0.8 mm, this is what is used, and an RF frequency of about 25 megahertz, you get about 2 to 4 megahertz of oscillation frequency. That is important in the next slides, because that is going to tell us what kind of, how to updo these gates and all that. And along the axis, you get about 1 or 2 megahertz for a very high voltage of about 1000 volts applied to this. So this particular trap, at some point I'll show you what the size is. Now there are many variations of this linear trap. So the IMQ and this Honeywell and some other companies, they use traps which are like that. It's a planar structure where you basically unfold these electrodes. If you look at topologically what it is equivalent to, this trap is equivalent to this linear trap which is unfolded on the surface. And you apply radio frequency along these two electrodes and a static, or the vice versa. You apply basically RF between the central one and the outer electrodes. And these additional electrodes are DC electrodes to confine the atoms along this line. Okay? And they can also be used to split the chain of ions, move them around and bring them together. Dimensional blades kind of a structure, and you can also make it with rods and these rings. So these rings are basically handicap electrodes to confine the ions along the axial direction. Now what I'll do is I'll take an example of one particular ion trap, and especially this from Innsbruck, and show you how one can actually do this quantum computing operations on these ions. So most of these experiments are from this particular group, so I may not cite on each slide, but wherever, if there is something belonging to our group, I will tell you. But I'm giving you this example since I worked on this particular trap long ago. Okay, so the entire system looks big. Of course, now things have become more compact. This is 20 years ago. Now you have these lasers in a rack, and the ion trap and everything sitting in a small, maybe half a meter cube kind of a box. You have the trap, you have all the optics, everything. Lasers in a rack, light coming from optical fibers. Here there are all free space lasers, and the trap sits inside this ultra high vacuum chamber. The pressure is below, way below 10 to the power minus 10 torrs. And inside that you have the linear trap. Just to give you the idea of the size, the distance between these two tips of the end caps is about 7 millimeters. So this is about 7 millimeters. So that's the scale of this trap. And there you have the ions which are trapped, which you basically do. This is image through a high numerical aperture objective with very good resolution, less than a micron resolution, and you basically you do the quantum state manipulation. It's not moving. It's not moving. Yeah, so each of these ions, you decide on which particular levels you want to use as a qubit. And in this case, it's a S half to D 5 half transition. Now this is a spectroscopic notation for the electronic state in an atom. So it's basically angular momentum is 0 and the J value is half. Here the angular moment L value is 2 and J is 5 halves. Okay, so this is a metastable transition. It is not, this transition is not allowed by dipole selection rules, but higher order transition probabilities are allowed. So it's a quadrupole transition, it's called. So the lifetime of such states is very high, much higher than the dipole transitions. Some of you might recollect some atomic physics. Okay, so first thing is, those pictures that I showed you of these nice ions stable in free space, right? When you load ions, you don't get such a crystal. It's called a Coulomb crystal. Because the ions are hot, they are moving around very fast. You have to first cool them down. So the way the cooling is done is using lasers. And in this particular ion case, you use this 397 nanometer light, which excites this S half to P half transition. And it has a very, it scatters photons at a very fast rate. So the lifetime here, the line width is about 20 to 30 megahertz, exact number I don't know, it's between 20 and 30 megahertz. And you scatter photons very rapidly, and thereby what you do is that you transfer momentum from the photons to the ions, and then you reduce the kinetic energy, reduce the temperature, and then once the kinetic energy goes below the Coulomb repulsion energy, the ions suddenly crystalline, and you get a nice beautiful chain of ions. And then there are some additional transitions which are not essential for this discussion, which are used for doing some repumping and all that. Now this is the qubit transition, which is at 729 nanometers. Now this laser has to be very, very narrow, line width wise. It has to be of the order of few hertz. Only then that decides how good your error rates are on the qubit, because as Mr. Raghavan told in the previous talk, that this delta phi that you induce in the states, which causes these errors, to reduce that, to minimize that, this line width has to be much narrower. Now, this is for one particular isotope of calcium, that's 40, and we are also having a calcium 40 ion trap in our lab. I'll show some pictures of the ion crystals from the lab. There is another species, another isotope, 43, where there is a ground hyperfine structure in the ground state, which can also be used as a qubit transition, and there the frequency is 3.2 gigahertz. So by using either microwave or a pair of Raman lasers, which basically you have two lasers going from this level to this level somewhere up there, whose frequency difference is exactly this, you can do a qubit transition. I mean, you can basically change the state of these two qubits, so that also you can do. And this kind of qubits have larger coherence time, and they can be faster than the optical transition. Now, as I said, these are the two ions. The way you detect the state, whether you have excited, whether your ion is in the ground state or excited state, whether it is in 0 or 1, you can detect it by shining this 397 nanometer light. And if you see the ion, if the ion is sitting in this state, you see it bright. If it is sitting in this state, you see it dark. And this is the picture of both ions in the S state, ground state. So you see fluorescence when you turn on the 397. The other ion is in the excited state, so it is dark. This ion is in the excited state, so it is dark. Both ions are in the excited state, so both are dark. So this is a readout. In case of ions, by shining this light, you do a readout of your quantum state. I told you about this ion chain. When you shake them, they will start oscillating. I mean, you will have all kinds of modes, breathing mode, there is a center of mass motion, and these ions can go zigzag. All these types of modes of this chain of ions, they will lead to, depending on which particular mode you choose, you have to choose one particular mode for your quantum computing in order to execute 2 qubit gates. So what happens is that you have these internal states S and D, 0 and 1, and then you have the harmonic oscillator levels, right? Now these two create a ladder of combined states, okay? So this is where your ion is in the ground state, this is where your ion is in the first excited state of the motional mode, second excited state of the motional mode, and so on. Now, what happens is that if you come with a laser frequency exactly resonant to on S to D, you will only excite the internal state. So that is called as a carrier. Now, since this energy level is modulated by the trap energy levels, the motional modes, you get these side bands, red and blue side bands. Okay. So when I come with a light whose frequency is the sum of this frequency internal excited state and the sum of say and one motional mode's frequency, it's higher in frequency. So what happens is that internal state will go to excited state, plus you also excite one motional mode. So you also set the chain into oscillation, plus you excite the internal state. So these are blue sideband transitions. Now if you come with a red sideband frequency which is lower by one motional mode quanta frequency, if your ion is somewhere in the excited states of the harmonic oscillator energy levels, you keep coming down to lower. So if you excite with a red sideband, you lose one quanta of the motional mode. And then if you keep repeatedly doing that, if you are somewhere in the highly excited states of the motional modes, you keep coming down to the lowest motional mode. So this is called as a sideband cooling. So this is essential to start your quantum state preparation and quantum information processing. So first you have to come down because initially your ion is hot. Even though it is the energy is lower than the Coulomb repulsion energy, it still might be in a higher, maybe 10 to 50 N values. You have to come down. So you do the sideband cooling. So yeah, so this is just to say that if your kinetic energy is smaller than the energy difference between these harmonic oscillator energy levels, your motion is quantized, and then you can apply you can do second quantization and write the creation and annihilation operators for creating one motional mode or destroying one motional mode. So these are in terms of the operators, the position and momentum operators and okay, I'll just leave this. But okay, so this is what is important. So once you have an ion in the trap, you need to find out what this sideband frequency is. So if you scan the frequency of this transition, you get a carrier and different axial modes. Now you have to sit on one of these modes to do your coherent manipulations. Now, for example, if you want to do a single qubit operation, you are basically operating on only the S to D transition. Now you come with that 729 nanometer light which is tuned on the carrier, and you leave it on as a function of time. The excited state probability goes through this oscillation, and this is the Rabi oscillation. Now, depending on what this oscillation time is, if you choose this much time of the pulse, you completely excite the state from 0 to 1. So this is a pi pulse. Now if I come with a pulse which is only of this duration, this is my pi by 2 pulse. You create a superposition of ground and excited state. So initially in the calibration sequences that go on for characterizing the qubit, which Vishal talked about in the morning, this needs to be done for each qubit first. And also one has to do it for the blue sideband. The blue sideband oscillates much slower. So once you have these two, the data for these two, for each of the ions, now you define your pi by 2 pulse, pi pulse based upon this time. Now all this goes into the initialization and calibration stage, and then later you just fix the pulse width at whatever time and you start executing your quantum circuit. And then using this, people have created all kinds of things. Many two-particle Bell states, this controlled NOT gate, entangled many ions, not only 3, 8, 15 ions entanglement, and lot of things have been done with these. Now I thought of showing one, I'll show you one example of creating a two-ion Bell state, how it is done using this carrier and sideband pulse, and then I'll stop there. Just give me 5 minutes. So I'll talk about how to create this two-particle Bell state with just 2 ions in a tray. Because this is important, because that is, entanglement is one resource which you use amongst multiple ions to execute quantum circuits, which may help you solve certain problems. So what do I mean by two-particle Bell state? So basically we have 2 ions. Each ion can be in the ground or excited state, S or D state. So these are the labels for the excited state. These are 2 ions. So one ion in ground state, one in the excited state. So states like that. So you see this SS plus DD, SD plus DS, SS minus DD, SD minus DS. This kind of pairs, how do you generate these entangled states? With 2 ions. So with 2 ions, say you have 2 ions, right? Now you focus the light on one ion. Initial state is both ions are in the ground state. This is an initial state. And both ions are pulled to the lowest state of the vibrational state, which is, this is a motional state which is in 0. These are the 2 ions which are in both ground state. Now you come with a blue pi by 2 pulse, you apply on one ion. So what happens? This ion goes from, you create a superposition of this and this. So you induced one motional state, and you also created a superposition of S and D. So you get this state. Second ion state is the same. First ion state has created as a superposition, but you also have one motional mode. Okay? Now you have to get rid of that motional mode. Both ions have to come back to the ground state of the motional mode. Then you create this, what you do is that you point your laser on the second ion and apply a pi pulse on the carrier. So what happens? So this second ion goes to D state. Okay? Motional mode is still there. Now, you have to get rid of the motional mode. So you apply a blue pi pulse. This ion doesn't go anywhere because it's already in the S state, whereas this one comes back here, this particular D state. So you have this SD plus DS, and your motional mode is in the 0 state. So you created a Bell state, SD plus DS, by doing this. So you entangled both ions. Now you can do this by changing the phase of the pulses, carrier pulses. You can create various states. So this is a sequence of pulses that you apply on this initial state. A blue pi by 2 pulse with a phase of minus pi by 2, carrier pulse, and then a blue pulse, blue pi pulse, and so on. By applying this 3 pulse sequence with different phases, you can create SD plus DS, SD minus DS, and so on. Okay? And then you basically do a full tomography of this state and create the density matrices. That's how you create two ion Bell state. Then you can also do controlled NOT gate between the 2 ions using the same principles, using blue sideband pulses, pi pulses on the carrier pulses, you can create a controlled NOT gate. Once you have a controlled NOT gate and the single qubit rotation, then you can execute all kinds of gates with that. Yeah, that's it. Thank you.
Like topologically they have to place together, and how do we get all-to-all connectivity?
So all-to-all connectivity, you can also common motional mode. All ions will oscillate. So you can target the first ion and the last ion. You can connect, and that way you can connect. And there are these additional different other types of gates like Molnar-Sorensen gate and all that, where independent of which motional mode you are, you can use the motional modes to actually entangle different types of ions. And all-to-all connectivity, another thing is if you have a surface trap, you can move the ions
Yeah,
around.
surface, but if we are putting linear, then it would be.
In linear chain also you can get connectivity between different ions within the chain, because you still have modes where all the ions can oscillate together. So and then you target the one which you want. First you excite the say endmost ion, the last ion, and then you excite this motional mode, and then use sidebands to target a particular ion somewhere in the middle. That you can do.
For ion level, means micro level, nano level,
In dimensions or
microscopic.
temperature.
No, means in the system, because we are using spring dashboard model, physical in micro level, where I can see that my spring is my what we call analog computer, yeah, and my dashboard 0s 1 is my binary computers. So we got analog system and they got digital system. Now ions I cannot see by by eyes. So you mentioned about nano level couple of times. So nano level we are exciting means we are feeling it, something. Means we are either giving electricity signals or exciting means giving it signals. Laser we giving energy at nano level. And this all blue, see 360 degree now. We got 360 cricket uses that concept. When we excite the blue pi by 2 means I already eliminate the negative band. So I'm working in positive environment. And blue plus 180 degree and carrier is 180 degree. So that is in 360 degree. So I'm talking about reality. What is it manual, literally there. And now we are talking nano level and ions level. If that interpretation is correct?
If you are talking about time, the time required for executing these pulses is in the range of few tens of microseconds. And the physical extent of the wave packet of these ions is in the range of few tens of nanometers. So these are the different dimensions that are involved in this particular system.
Because it's for an atomic level and molecular structure.
Yeah, so few tens nanometers. Experiments. So which you do in a second. In 1 second you do 100 experiments and you create one data point.
So it has to interpret a result. We need to have a local resolution, spatial contour, or some place.
No, nothing. You just look at whether a particular thing is in excited state. So this, for example, it's either dark or bright. That's it. You have two answers, and just 1 second. from our trap in the lab. So these are different ions, and the way the state, for example, okay, this is again up to 11 ions. Our imaging system is not good because we are looking for some optical lenses. This is some jugaad at the moment. So this is an image of video of 3 ions, and you can see sometimes one of them goes dark, one of them remains bright. So these are the quantum jumps. I mean, whether it's either in the S state or the D state. So you do measurement 100 times and get 1 point. So for each quantum circuit, you execute it 100 times, 1000 times, depending on the gate, the speed and what qubit you use, and then you get 1 data point, and then you keep repeating that. So which is normal for these experiments.
So on the graph, actually, there are points.
It has an error bar.
It will
No,
deviate
no,
every
so spread along y and x axis.
So because
Depending
of
on-
computation repeatability.
Yeah. So that's where these, and then you characterize this state preparation and measurement errors, fidelities, all these you characterize from that experimental error bars that you get. So 100 times if I prepare the state in D state, if I get all the 100 times I prepare it in D, then it's, my preparation error is close to 0, or 1000 times, or maybe 999 times if I get the same, get the D state, excited state when I apply pi pulse.
So actually, there were 2 concerns. First was, which you mentioned, that multiplication of 10, 100, 1000. There should be some pattern of the on the graph. It should repeat. So how, I mean, that will be helpful.
So, no, so completely from 0 to 1. And every time I apply pi pulse, it should go to excited state, which doesn't happen because of lot of things. Now, in experiments, whenever you do experiment, there are 2 types of errors that you get. There are statistical errors, there are systematic errors, correct? Now this, if the errors are purely statistical, then the spread is uniform of the values that you get. And you get some kind of a Gaussian distribution of around some mean value with some spread. Now the spread, the smaller and smaller the spread gets, your accuracy increases. Now, and then there are other, you don't have control over, you only can characterize and see what is the trend as a function of certain parameters that might be affecting the value. That you have to characterize and imply.
So which kind of, any algorithm you will suggest that, or you have found out which has proved to be more useful or more repeatable, giving more reliable result over the time, tending towards more.
So I can't talk anything about algorithms. All I can say is, from an experimentalist point of view, you try to minimize all possible sources of noise in your system. Like, for example, since I am detecting photons to decipher the state of the qubit, my imaging system has to have very high throughput. I should ideally be able to collect all the photons that the atom is emitting. And atom is emitting in 360, this entire 4 pi solid angle. But my imaging system only will collect a portion of that solid angle. Now I have to maximize that. How many photons I collect. The detector has to have very good quantum efficiency. And your laser has to have very little noise. Its stability should be very good, frequency stability. If the laser frequency moves around, the counts will go down. All these add up to the entire budgeting of the noise in your system. So all these we have to take care. And then I will say that, okay, I have these basic building blocks now. These 2 qubit gates, this single qubit gates, and this is how I can connect from one ion to the other. Now you tell me what circuit you want to execute. Quantum circuit. Now I will break that down, break that quantum circuit into my 2 basic gates, and then I execute it on the ions. And then whatever result I get, then you have to interpret it back and see what
So just one question. So the distance,
reading is.
They will be placed automatically. If cavity is there, it will automatically adjust.
No, this is not cavity, this is electric field that you use to confine the ion. You increase the axial potential, you compress the chain, and you increase the frequencies of oscillation.
And individual atoms with the sign inclination beam.
Yes.
So you have thousands of atoms, thousands of beams.
No. So if you are scaling up to 1000, your geometry is different. You have a region where you store them, you bring them down, bring them with electric fields, move them around, bring them into a region where you are doing the imaging. Read out.
And but at one point, only one photon will absorb, right? But how much in
Of a particular ion, particular transition. Like for the 397, I think it's a few milliwatts per centimeter square of intensity for saturating the transition. So you cannot, so there is the parameter is the saturation intensity. It's several milliwatts per centimeter square, that kind of intensity you need. So it basically amounts to using 50 to 100 microwatts of laser light on this chain of ions, not much.
Thank you, sir, for that captivating presentation. Your insights into atomic physics and quantum technologies have illuminated the exciting possibilities and have increased our understanding in this field. I now request Shri Vivek Nanwal to please felicitate Dr. Umakant Rapol.